Hey guys, welcome back to another video. I know it's a different format today. My pen died, my digital pen died at the start of lecture. And so today we're going to be doing it on paper. I made my notes on paper and we're going to be looking through it on paper. So today we're going to be looking at representing functions as series. And afterwards, we're going to touch on a little bit about, if I can find it, we're going to be working on Maclaurin and, Maclaurin and Taylor series. There, Maclaurin and Taylor series. So let's see what it is. So as we touched on at the end of the last episode, we can represent functions, whatever the function is. For example, 1 over 1 minus x squared. We can represent that as a series, right? And most commonly, we're going to do it as a power series. So a power series is when it's Cn x minus alpha all to the power of n. So let's look at what we can do. So first of all, we have the function fx is equal to 1 over 1 minus x, all squared. The thing with this is that when you have a function, you can do function things to it, right? With a function, we can integrate, we can differentiate, right? So the idea is that we can notice these things and then try to apply it and then do function things to it and then turn it into a series. So how are we going to do this? Let's try this first. So when we have 1 over 1 minus x squared, right? We can do 1 minus x all squared. What we realize is that it's actually the differentiation of 1 over 1 minus x. If you think about it, 1 minus 1 over x is just 1 minus x all to the power of minus 1. You differentiate this, multiply by minus 1 on the outside, then multiply by the differentiation in here, another minus 1, and then decrease the power by 1. That's what you have, right? The minus 1s and minus 1s cancel out. Then you have 1 over 1 minus x all squared. So what we notice, we can say that this is just the differentiation of 1 over 1 minus x. And if you remember, this is the form of the sum of a geometric sequence, right? If you had, like, for example, 1 plus r squared, pin my paper down with it, 1 plus r squared plus r cubed, the sum, the infinite sum of this, right, the sum of all of this is actually equal to 1 over 1 minus r. So the fact that we have 1 over 1 minus x tells us that we can represent this as the sum of a geometric sequence, but instead of r, we have x. So there it is, right? The sum to infinity of x to the n, right? X is the common ratio. X can be any number, and that's going to be the common ratio, and that's the geometric sequence. So we go from a function. We notice that's a different differentiation of this. Then we notice that this is actually equivalent to the infinite sum of a geometric sequence with common ratio x. Now what's next? We realize that, okay, let's write it all out like this. The geometric sequence can be represented as 1 plus x squared plus x cubed. And then we can use the differentiation as before, and we differentiate everything here, right? 1 differentiates into 0, x differentiates into 1, x squared differentiates into 2x, etc. So what we end up with is we notice that, oh, there's a sequence that's in this form, and that's exactly in this form, right? Cn x minus alpha, in this case alpha is 0. But what you end up with is actually, it's n multiplied by x to the power of n minus 1, right? At 0. At 0, right, there's nothing here, and then at 1, it's 1 multiplied by x to the 0, so that's 1, and then that's 1, and then plus 2x, n is 2, so 2 multiplied by x to the 2 minus 1 is 1, so 2x, right? So that's the idea. We went from having a function down into a sequence. And yeah, that's it actually. So that's it for this function. It's just to show you that, yes, you can say that it's a differentiation of something and then represent that as another series and then do all these kind of things. Okay, so let's keep looking at this. So we have this function here where it's ln of 1 plus x. So what we notice here is that ln of 1 plus x is equivalent to the integral of 1 over 1 plus x, right? If it's 1 over 1 plus x, we integrate it, that's ln 1 plus x. So and then we can see that 1 over 1 plus x, we kind of want this geometric sequence, geometric series kind of like form, because that's what we're familiar with, right? So how do we turn this, what we have is 1 over 1 plus x. How do we turn that into the form here where it's 1 minus 1, 1 over 1 minus r? Well, if it's 1 plus x, we can also say that it's 1 over 1 minus x. It's 1 over 1 minus something, right? 1 over 1 minus r. We want to represent that the same thing with x, so we say it's minus x. So therefore, we can say that this geometric sequence is the same thing as the infinite sum of minus x to the n, right? It's just a geometric sequence, but then with minus x as the common ratio. And when you have minus, you can say it's almost like minus 1 multiplied by x, all to the power of n, right? And when you take this out, it's minus 1 to the n multiplied by x to the n. So what you can end up saying is you can split it out, and then it turns into an alternating series. Obviously, this was the geometric sequence, and you must say that the common ratio must be less than 1. And in this case, x or minus x, but if you do absolute values, it's just x, must also be less than 1. So that's why I say it here. But yeah, it's an alternating series here. And so if we say that 1 over 1 plus x is equal to this through all these steps, then that means that ln of 1 plus x equals the integral of 1 over 1 plus x. Therefore, ln of 1 plus x must be equal to the integral of whatever is equal to that, which in this case is the series that we found, right? This alternating series. We notice that this here is just a constant. Whatever it is, I'm actually not sure what it's equal to, but it's just the infinite sum of the alternating of minus 1 to infinity. And that's a constant. We can take that out of the integral sign. And then that's just the integral of x to the n dx. Then you have ln of 1 plus x is equal to the sum of this multiplied by x. The integral of this, you increase the power by 1. That's x to the n plus 1 divided by the new power. That's n plus 1 at the bottom. And then plus c. And this isn't over yet. What we're doing next is we have to find what c is. Oops. This one, yes. Okay, we need to find, my gosh, so sorry, not used to paper. Okay, we need to find what c is. So what we end up with is this equation here where x belongs to the range not inclusive of minus 1 or n to 1, right? And now what we have to find is we have to find what c is, because this equation here, but then what's this constant? Well, if we let x is equal to 0, the left-hand side is ln of 1 plus 0 is ln of 1, which is equal to 0. And the right-hand side, if we let x equal 0, that's 0 to the power of something, that's 0. 0 multiplied by this, that's all 0, so that leaves c by itself, 0 plus c. Therefore, c is equal to 0, and c is nothing. So now we can represent the final function as just this without the c. Basically, it's this without the c, which I find is really interesting. Okay, so let's move on to the next example here, where we let fx equals arctan x. So if we realize the integral of 1 over 1 plus x squared dx is equal to arctan x plus c. So what we can say is if we want to find what arctan x is equal to, we rearrange stuff to do it. And that's what we do down here. But really quick, let's find what 1 over 1 plus x squared is, right? We want it, again, in that geometric form where it's 1 over 1 minus r, right? And so what we say here is it's 1 over 1 minus x squared. And then we do the whole geometric sequences again. It's instead of being x to the n, it's x to the 2n because it's x squared to the n. And then you take the minus 1 out again. And x squared must be less than 1, therefore x must be less than 1, the absolute values of that. So we do all the same things as before. What we end up with is arctan. Remember, arctan is equal to the integral of 1 over 1 plus x squared. What did we find is equivalent to 1 over 1 plus x squared? We say arctan is equal to the integral of whatever is equivalent to 1 over 1 plus x squared, which is here. And then we minus c. You don't have to minus c, but I just do it for consistency. So you can see I move the c over this side. But yeah, again, we can take whatever this is out because it's just a constant, right? It's just a number. I don't know what that sum is. It could like even be divergent, but because it's just a constant, we can take it out. And then it's the integral of x to the 2n dx minus c. And then when you integrate x to the 2n, first of all, the integral is you increase by 1, do that, bam. And then when you integrate, you always have a plus c term. So the c term is here. So again, x, this is just coming from here. And we want to find, again, what c is. So we let x is equal to 0. Arctan of 0 is equal to 0. And then on this side, if we let x equal 0, 0 multiplied by all this cancels out. It leaves just c. c equals to 0. So therefore, the final representation has no c. And it's just saying the function arctan x is equal to the sum of this series here, alternating series of x to the 2n plus 1 over 2n plus 1. Okay. this is, I think, another example. I think this one was actually pretty interesting. So, and this is the last one before we move on to Taylor series and Maclaurin series. But basically, this is the integral of 1 over 1 plus x to the 13. Okay, we do the same things. Let it equal to all of this. But remember, this time, actually, I'll go with this and then I'll say what's different about this one, okay? So this is fx is equal to this. We want to find what fx is in terms of series. So let's look at this first, 1 over 1 plus x to the 13. We do the same thing. We want to form 1 over 1 minus r, right? And so that's going to be 1 over 1 minus x to the 13. We do all those kind of stuff. We get this geometric sequence that is also alternating, x to the 13n. And then what we end up with is that this is, you have to integral, right? Fx is equal to the integral of whatever we found was equal to this, which is this. So the integral of this. So therefore, this is fx, the integral of 1 over 1 plus x to the 13 is equal to the integral of what 1 over 1 plus x to the 13 must be equal to. Again, we can take this, whatever this is, it's a constant, we can take it out. The integral of this, you do all that kind of math. And then it's basically pretty similar, but what you notice is that we don't find c. We don't find c. And the reason why we don't find c is because when you integrate, right, if you integrate like 1 dx, the answer is equal to x plus c, right? This is an integral. You integrate this, you find something, and then it's also a plus c. So that's why we don't find c in this case. If you do c, it turns out to be, I think, like equals to 1. I think I messed up. I tried to do it in class, but then I asked the teacher and he said no. Because actually, and then I realized, yeah, it's an integral, so you don't find the c. The c inherently exists if you do an integral. So if you notice that, don't do c. That's just kind of like a note for you to keep in mind, is that because this is an integral and we're finding what this is equal to, we're basically doing the integral, then we must keep the plus c here because the integral has a plus c. Okay, so let me just take these over here. Okay, so I think now we're good to move on to Taylor and Maclaurin series. And basically, let me run you through this. So first of all, the conditions for a Taylor and Maclaurin series is if you have a function that's equal to a power series like this, right? Just like how we represented things before. That's equal to c0 plus c1 multiplied by x minus alpha plus c2 multiplied by x minus alpha squared, right? You get the pattern. And we know that fx is differentiable. That's the kind of condition to be able to do a Taylor and Maclaurin series, is that fx needs to be differentiable. Or it needs to be like differentiable all the way through. So therefore, when we do f dash x, that's also a power series. We proved that in the last video. But basically, if you differentiate this, that turns into 0. But then this is c1, and then this is c2, 2c2, right? The 2 goes forward here. And this is 2c2 x minus alpha to the power of 1. And then it's still a power series, right? And then you can do it again. You know, f double dash x, and that's also a power series. You do f triple dash x, that's also a power series. So you keep doing that. That's the kind of foundation for what we're doing with a Taylor and Maclaurin series. So the condition is that fx needs to be infinitely differentiable. And another way to say that is it's a smooth function. Okay, but basically it needs to be infinitely differentiable. So what's going on here? Why does it matter? So if fx is equal to this, that's just the power series form that we've seen. How can we find the coefficients? How can we find what this is, and what this is, and what this is, right? What you do, first of all, you think, let's put in fx equals alpha, right? Fx equals alpha, sorry, not fx equals alpha, we put in f alpha. So we use alpha in place of x. What happens here is we have c0, okay, plus c1 multiplied by x minus alpha, but instead of x, we have alpha, so it's alpha minus alpha. That's 0. c1 multiplied by 0 is 0, right? Alpha minus alpha is 0. 0 squared is still 0, c2 multiplied by 0 is still 0. So by putting in alpha, f of x, the 0th differentiation, we can find c0. How do we find c1? Well, if you differentiate c1, I just explained this part here. But if we differentiate c1, right? If we differentiate fx, my bad. So f dash x, that's going to be equal to, right? c0, that's a constant. When you differentiate, that goes to 0. So it's not there. And then you have c1 by itself, because c1 here, if you multiply by c1 multiplied by x, c1 multiplied by alpha, that's a constant. That also disappears. So it's c1 multiplied by x. You differentiate that. Then you get c1 by itself. And then you get 2c2x minus alpha, etc. But if you put in alpha, f dash alpha, what you end up with is c1, okay? And then alpha minus alpha, that's 0, so nothing else at there. So by going, so on the 0th differentiation, if we put in alpha, we get the c0 term. If we're on the first differentiation, we put in alpha, we get the first c1 term. And then so on, you go so forth. So you can get c2 by doing f double dash alpha over 2 factorial. And you can get c3 by using f triple dash alpha over 3 factorial. So you can see how the idea of the Taylor series is that if you have a power series and you use the infinite differentiations of it, you can get the coefficients c0, c1, c2, c3, c4. So that's the idea. And so let's give you a few definitions first. So therefore, the power series of fx in this case is related to the derivatives of f at alpha. And so a way to represent a Taylor series here is that fx is equal to this is the power series. If you can represent fx as a power series, then you can also represent it as the infinite sum of f and the nth differentiation passing through alpha over n factorial multiplied by the same thing as on the right side here. We're basically just finding Cn. So that it just replaces Cn. You still have the same x minus alpha to the n. This is called a Taylor series of f at alpha. So if you're passing alpha as an argument as to f, then you're saying that the function is at. So it's the same idea as like you have a function here. What is its value at alpha, right? Alpha is just a value of x. So this is a Taylor series at alpha. And moving on, a Maclaurin series is just a special case of a special case of Taylor series where alpha is equal to 0. So instead of putting in alpha, you put in 0. It's the same kind of thing, but it's just when alpha is equal to 0. So let's look at a few examples, and this should be close to a wrap as well. So fx, let's say we have fx is equal to 1 plus x squared, right? We want to write down its Taylor series at 1, meaning that we pass through alpha equals 1. So how we're going to do this? First of all, we have the 0th differentiation of fx right here. f0x is equal to 1 plus x squared. The first differentiation, f single dash x is equal to 1 plus 2x, right? This goes to 0, 1, 2x. F double dash x is equal to 2. So if the function is represented by the infinite sum of f and the nth differentiation passing through alpha, which in this case is 1, over n factorial multiplied by x minus 1 to the n. So what we end up with is that, and keep in mind, x here is not the same as this x, okay? Actually, no, this is the same x. My bad, because we can represent this as a series of x, so this x is the same x. Okay, so now we need to see what f0 passing through 1 is. f0 is equal to 3. When n equals 1, the first differentiation passing through 1 of it is also 3, right? You put, first of all, so the 0th differentiation, this one, you put in 1 through the argument, so 1 plus 1 plus 1 squared, that's 3. Okay, f single dash and passing through 1 is right here. You put 1, okay, 1 plus 2 multiplied by 1, that's 1 plus 2, so that's 3. So that's also equal to 3. And then f double dash, we pass through 1, so f double dash is equal to 2. You pass through 1, there's no x here, so it doesn't matter. It's equal to 2. So now we use this form and we say fx is equal to, when n equals 0, you put derivative 0th differentiation value at 1, so that's 3, over 0 factorial, so we put 0 factorial, multiplied by x minus 1 to the n, right? 3 over 0 factorial, which keep in mind, if you don't know, is equal to 1. And then x minus 3 to the 0, that's also equal to 1. So 3 over 1 multiplied by 1, that's 3. Next, you have n equals 1. So you have 3, right? We found 3 when n equals 1. 3 over 1 factorial multiplied by x minus 1 to the power of 1. 3x minus 1. And then when you have n equals 2, we found that when second differentiation is equal to 2, 2 over 2 factorial multiplied by x minus 1 to the power of 2. So 2 factorial is equal to 2, 2 over 2 is 1, so you have x minus 1 squared. And then the reason why we don't keep going is that the triple dash, the fourth differentiation, or the third differentiation, I suppose, is equal to 0, right? And then the fourth one is equal to 0, and the fifth one is equal to 0. So technically, yes, it's also equal to 0 plus 0 plus 0, but it doesn't matter because it goes to 0 there. So really quick question, what is the radius of convergence and the interval of convergence for this? Well, if you're kind of smart-eyed, you would have seen the answer here, but the radius of convergence is equal to infinity because there's only 3 terms. You could pass in any x, right? X equals 100 billion, and it would still converge because there's no extra terms at the back. It's just 3 terms. So even a really large number, you add them together, that's still convergent. And then therefore the interval of convergence is x belonging to any real number. Okay, let's look at a few more examples. So now let's look at the Maclaurin series for fx equals e to the x. This is, again, the zeroth differentiation of e to the x. Remember that Maclaurin series is just a special case where alpha is equal to 0, which means we still use the same form here, except that it's f to the nth differentiation putting through 0 instead. So let's look at f, how this changes when we differentiate e to the x. It's f single dash x is e to the x, f double dash x is e to the x. So it doesn't really matter. If we pass through 0 as the argument, e to the 0 is 1, this one's 1, this one's 1, so they're all going to be 1. So if we write out this form, it's always going to be technically 1 over 0 factorial plus 1 over 1 factorial multiplied by x minus 0, so it's just x. So you can see how it's constantly 1, so we don't really care about the 1s because e to the 0 is 1. And then you have x to the 0 over 0 factorial. That's x over 1. That's x to the 0, but then x to the 0 is 1, so that's 1 over 1, which is equal to 1. X to the 1 over 1, that's just basically x. I shouldn't write this. It's just x. And then you have x squared over 2 factorial, x cubed over 3 factorial. It's really interesting. But then we need to look at the radius of convergence and the interval of convergence. And basically, we can find that using a ratio test. So basically, if you remember, a ratio test for a power series needs to look at the coefficients, right? So if the function here, the coefficient here, if you had, like, let's say, sum of 2n x to the n, right? The coefficients is this one. Meanwhile, the x minus alpha bit is this one. Because if you remember, it's cn x minus alpha to the n. So we only want to look at the bit that doesn't have the x, which is 2n. So in this case, the bit that doesn't have the x is this, fn 0 over n factorial. This is the bit with the x, so we don't look at this. So this is cn, right? And cn, well, if you think about it, because this is always going to be e to the 0, which is 1, it's just 1 over n factorial. So if we do cn plus 1 and over cn, that's 1 over n plus 1 factorial over 1 over n factorial. And then you do all those kind of stuff. I did this from last video, but basically you represent it like this. You cancel everything down. It turns out to be 1 over n plus 1. The limit to infinity of that is 1 over infinity, which is equal to 0. And since the radius of convergence, we did this in the last video as well, is equal to 1 over L, therefore it's 1 over 0 is infinity. And so therefore, any value of x is convergent. And so this function exists, e to the x exists on any value of x, right? And that's true because e to the x goes from negative infinity to positive infinity x. It exists on every x function. If we, for example, were to represent, I don't know, like tan x, right? What you realize is that at pi over 2, it's not going to exist. So on the interval of convergence, it would be like every x value except pi over 2 plus k. So yeah. That's what it means. I think this is the final example we have, is the Maclaurin series of sine x. So again, f to the 0 x is equal to sine x. F dash x, we differentiate that cos x. F double dash x minus sine x. F triple dash x is minus cos x. F quadruple dash x is equal to sine x. F fifth differentiation is equal to cos x. It repeats itself. And when x equals 0, because we're looking at a Maclaurin series, that's going to be sine of 0 is 0. Cos of 0 is 1. Sine of 0 is again 0. Minus cos of 0 is minus 1. Sine of 0 is 0, cos of 0 is 1. So it repeats 0, 1, 0, minus 1, 0, 1. And this is basically, if we represent it like this, we can try to write out every kind of possibility, but it basically turns into, right, 1x to the 1 over 1 factorial 0, so it cancels these things out, these things don't matter, and then 1 plus 1 should be 1, then minus 1, so I think I wrote this as a minus, yeah, this is a minus, minus x cubed over 3 factorial. Remember, this one is just this one from here. This is minus 1, so that's why this is minus 1. But x cubed over 3 factorial plus 1 x fifth. So you kind of skip out on every even number, right? 0 to 4, you turns into 0. So the final form is x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial. And we can kind of see that it can be represented in this form here. It's an alternating series because it's positive minus, positive, minus, and then x to the 2n plus 1 over 2n plus 1. So it's just odd numbers here. 2n plus 1 is the odd numbers factorial. And we do the same thing, same ratio test. I gotta go really quick, that's why I'm rushing a little bit. But yeah, you do the same thing as before, except we're using minus 1 over n over this, right? And that's the absolute value, so we can remove the minus 1. But it's 1 over 2n plus 1 factorial, because that's independent from x. Let me just do this really quick. So Cn is equal to 1 over 2n plus 1 factorial. And then the x part is multiplied by x to the 2n plus 1. So you can see how this is the part where we want to do the ratio test with, is what we do. And then we find that it all cancels out down to 2n plus 2. Again, put infinity, that's 1 over 0. 1 over infinity equals 0. And because the radius convergent is 1 over L, 1 over 0 equals infinity, then any value of x works. And that's true because for the sine graph, it goes from 0 to negative infinity to positive infinity. Every value of x works. So yeah, thank you guys for watching so much. I know it's a long video. Hope you guys have a good rest of your day.